question number 1, conductivity of or question number 11 actually, conductivity of 0.0024 molar acetic acid. So acetic acid concentration is given. Concentration of acetic acid is 0.00241 molarity. Okay, and for this solution conductivity is given. Conductivity of 0.0024 molarity, that is concentration, and conductivity value, conductivity means kappa, also called specific conductance, which is given as 7.896 into 10 to the power minus 5 Siemens centimeter inverse. Okay, the question is calculate its molar conductivity. Then one more question is asked, if lambda m naught, that is molar conductivity at infinite dilution for acetic acid is 390.5 Siemens centimeter square per mole, what is its dissociation constant? They are asking dissociation constant. Okay, see here, first we will calculate the molar conductivity. You know very well, molar conductivity lambda m is equal to, okay, see kappa value is given in centimeter inverse, right? Whenever kappa given in centimeter inverse, you must use this formula. 1000 should come in the numerator. 1000 kappa by molarity of the solution. Okay, 1000 kappa by molarity of the solution will give you molar conductivity. So the value is 1000 into kappa value is given 7.896 into 10 to the power minus 5 over molar conductivity is given 0.00241. Okay, you can take log and you can simplify this. I'll give the answer directly. It will come around 1000 into 7.896 divided by 0.00241. I am getting the value as divided by 345. I am getting a value which is 32.76348. It is coming, so I'll write 35. Okay, so this is the molar conductivity value, and the unit is Siemens centimeter square per mole. Okay, so now we found out the value of molar conductivity. Then the next question is, what is the dissociation constant of the acid? Okay, to find dissociation constant, right, you know very well, go to the next page. Yeah, you know very well, degree of dissociation alpha can be given as molar conductivity at a given concentration divided by molar conductivity at infinite dilution. Okay, once you know alpha, you can calculate Ka. According to Oswald dilution law, Ka is equal to alpha square C by 1 minus alpha. Okay, so if I substitute alpha square here, this is the alpha square value, which is lambda m by lambda naught square we have to take. So you will get lambda m square into concentration. That lambda m naught will go down, it will go to the numerator, denominator, into 1 minus alpha value is lambda m by lambda naught. Okay, if I take LCM, and if I simplify this further, I'll get lambda m square into C over if I take LCM here and if I cancel lambda naught, I'll get this formula, lambda m naught minus lambda m. Okay, so by substituting the value of lambda m square, concentration, and lambda m naught Okay, all the values here, you can calculate Ka directly, right? So how to proceed this? One second, I'm sorry, here I missed lambda naught square. Okay, so one lambda naught will be there outside. Yes. Okay, because in the numerator we have alpha square, so this is the value of alpha. Okay, if I take square, I'll get lambda m square by lambda m naught square in the denominator. Okay, and if you substitute all these values and you simplify, you will get this formula. So this is the formula we are going to use to calculate Ka. Okay, we already got the value of lambda m, right? What is the value of lambda m? See, 32 point. Yeah, the value of lambda m is 32.7635. Right? I am going to substitute that value here. Okay, I am going to substitute that value in this formula. Right? So what we'll get is, so what is the formula? Ka is equal to lambda m square. This is molar conductivity at concentration, at the given concentration, into C divided by lambda m naught into lambda m naught minus lambda m. Okay, this is the formula, right? If I substitute the values, I'll get 32 point, lambda m value is 32 point, what's the value of lambda m naught? 32.7635. okay, so I'll substitute the value as such, 32.7635 whole square into concentration is given here. Concentration of the solution is 0.00241 molarity divided by lambda m naught value is given in the question, which is 390.5 into 390.5 minus 32.7635. I just substituted the values that is given and with the value we have calculated. Okay, now if I simplify this, okay, you will get answer which is comes out as 1.85 into 10 power minus 5 roughly. Okay, this is the value of Ka. Note down. Is this clear?
Yes, sir.
Yeah. See, for this question, what is given? They are asking how much charge is required to convert 1 mole of aluminum 3 plus to aluminum. Okay, aluminum 3 plus gaining 3 electron and reduced to aluminum. Right? In this reaction, according to this equation, 1 mole of aluminum ion requires 3 moles of electron. 1 aluminum ion requires 3 electron. So 1 mole of aluminum ion requires 3 moles of electron. Okay, for complete reduction. Okay, 3 moles is nothing but, you know, 1 mole of electron carry 1 Faraday charge. So 3 moles of electron means 3 Faraday of charge. Okay, now let me go to the next one. Second one, question number 12. Second one is 1 mole of copper 2 plus 2 copper. Can I give the answer for this question?
2, sir.
Yes, 2 Faraday of charge. Very good. Right, to convert copper 2 plus 2 copper. Okay, Cu2 plus gaining 2 electron and become copper. So 1 mole of copper requires 2 moles of electron. 2 moles of electron means 2 Faraday of charge. Very simple. Right, then third one. To convert MnO4, 1 mole of MnO4 minus to Mn2 plus. You know very well, MnO4 minus, where oxidation state of manganese is plus 7. Okay, now it becomes Mn2 plus. Mn2 plus means we need to add 5 electrons. I am not balancing the equation. I am just focusing on number of electron required. That's all. Okay, my goal is not to balance the equation. So in the left hand side, manganese is present in plus 7 oxidation state. By reduction, okay, it is converted into Mn2 plus. For this reduction, you require 5 electrons. Correct? Plus 7 to plus 2 requires 5 electrons. So for 1 mole of permanganate, you require 5 moles of electrons. Therefore, what is the charge required? Students, how much charge is required?
5 Faradays.
5 Faraday, that's all. 5 Faraday. Right? So, it's a very simple question, direct one. Then, see question number 13. Question number 13. How much electricity in terms of Faraday is required to produce? Number 1. To produce 20 gram of calcium from molten calcium chloride. So we have molten calcium chloride, right? Molten calcium chloride is there. So calcium chloride solid, on heating it will melt and you'll get calcium ion liquid and chloride ion liquids. So it is molten. Then this calcium ion, by gaining 2 electron and reduced to calcium. Okay, reduced to calcium. Now the question is, to get 20 gram of calcium, how much electricity is required? What Faraday of electricity is required? Right? Very simple. See, according to this equation, right? According to this equation, see, 1 mole of calcium ion. Suppose if we take 1 mole of calcium ion gains 2 moles of electron and reduced to calcium 1 mole. And reduced to 1 mole of calcium. So to get 1 mole of calcium, you require 2 Faraday of charge. Okay, I'll write here 1 mole of calcium, okay, requires 2 Faraday of charge. 1 mole of calcium means 40 gram. 40 gram of calcium, okay, which is nothing but molar mass, right? 1 mole is nothing but molar mass. Molar mass of calcium is 40 gram. So 40 gram of calcium requires 2 Faraday of electricity, right? Then 20 gram requires how much?
1 Faraday, sir.
That's all, 1 Faraday of electricity, right? So this question is very, very simple. Take down 1 Faraday of electricity. And see the next question, 13, question number 13. 2. 40 gram of aluminium from molten aluminium oxide, Al2O3. Molten aluminium oxide. Okay, let's move to the next page. Yeah. So question number 13, number 2. Aluminium oxide, Al2O3, solid, which on heating, okay, melts and give you 2Al3 plus ion, okay, in the liquid state, and 3 oxide ion, O2 minus, in the liquid state. Right? Now each aluminium ion gains 3 electrons. Each aluminium ion gains 3 electrons and become aluminium. Okay. Now the question is 40 gram of aluminium, right, from molten aluminium oxide. According to this equation, to get 1 mole of aluminium, you require 3 moles of electron. Okay, 3 moles means 3 Faraday, right? And 1 mole of aluminium is nothing but equal to molar mass of aluminium, which is 27 gram. So 27 gram, to get 27 gram of aluminium, we need to pass 3 moles of 3 Faraday of electricity for 27 gram. To get 40 gram of aluminium, that's what they are asking. To get 40 gram of aluminium, how much charge is required? 3 Faraday divided by 27 into 40. Okay, so this is 9, 40 by 9. Can you tell me what will be the rough value? 40 by 9? 4 point? Roughly 4.44 something.
4.4, sir.
Very good. That's all. That's all. So the question is very simple. If it is given molten, okay, you will get only those ions, whatever ions present in the compound, only those ions will be available in the liquid, and only those ions get reduced. Okay. If it is aqueous solution, then you have to think about other reactions. Since it is given molten aluminum oxide, molten calcium chloride, the problem is simple. right? Yeah, now let me go to the next question. Question number 14. Question number 14. 14.1. How much electricity is required in Coulomb for the oxidation of 1 mole of water to oxygen? Okay, 1 mole of water to oxygen. Water H2O to oxygen. Right? Yeah. Students, what I will do, just for understanding purpose, we can split water molecule as 2H plus and 1 O2 minus ion. Water H2O can be split into 2H plus and 1 O2 minus ion. Okay, this O2 minus ion, observe carefully, O2 minus ion, right, release 2 electron and become oxygen atom. But oxygen atom is unstable, so 2 oxygen atom combine and form molecule. Therefore, I'll multiply this by 2 so that I'll get O2 and this become 4 electrons. I'll just multiply the equation by 2. So here I got 2 oxide ion, because each oxide ion release 2 electron, 2 oxide ion release 4 electron, that's all. Okay. Now in the left hand side I have 2 O2 minus, but in the first equation right hand side I have only 1 O2 minus. So I'll multiply throughout this reaction by 2. So 2, this will become 4 and this become 2. Now let me add them. If you add, you can cancel left hand side and right hand side. So what we'll get is 2H2O, okay, giving 4H plus O2 and release 4 electron. Okay, so when water molecule undergo this process, it releases 4 electron. Loss of electron is oxidation. So when water molecule undergo oxidation, it gives H plus ion and oxygen gas. Students, observe carefully. It gives H plus ion and oxygen gas. Now this is the balanced equation. To get 1 mole of oxygen, observe carefully. To get 1 mole of oxygen, okay, to get 1 mole of oxygen, okay, I'm sorry, what's the question? How much electricity is required in Coulomb for the oxidation of 1 mole of water? Yeah, so we need not worry about this now. Let me focus on the question. See, according to this equation, 2 moles of water to oxidize, it requires 4 Faraday of electricity. Am I right? 2 moles of water requires 4 Faraday of electricity. Correct? It's because the balanced equation. So left hand side, if you take 2 moles of water to undergo complete oxidation, you require 4 Faraday of charge. Right? So for 1 mole, question is 1 mole. For 1 mole of water, you require 1 mole of water to undergo oxidation, you require 2 Faraday of charge. 2 Faraday means 2 into 96,500 Coulomb. You know very well. 1 Faraday is 96,500 Coulomb. So if you multiply this by 2, you will get the answer. Okay? Take down. Is this clear? Any doubt? In Faraday it is 2 Faraday, but they are asking in Coulomb. So you just multiply 2 into 96,500, you will get the answer. Take down. Is this clear? Any doubt?
Sir, how did you get the second equation?
Yeah, listen, see, I'll read the question again. See, how much electricity is required in Coulomb they are asking for the oxidation of 1 mole of water to oxygen, right? So we need to convert 1 mole of water to oxygen, right? But we need to understand how water on oxidation gives oxygen. To understand this, okay, you must know these 3 steps. What is that? See, first you split water molecule into H plus and O2 minus ion. Okay, so I have balanced it already. So if you take two molecules of water, 2 molecule of water and ionization will give 4H plus and 2 O2 minus ion, and each O2 minus ion release 2 electrons. So we have 2 O2 minus ion, 2 O2 minus ions release 4 electron and become oxygen O2. If I add the 2 equations, 2O2 minus cancel, so you'll get 2H2O plus gives 4H plus O2 plus 4 electron. This is the oxidation reaction of water. Students, observe carefully. This is the oxidation reaction of water. You remember this reaction. If you remember this reaction, then you can write it directly in the examination. Even if you forget, then you can get it from this relay, from this steps. Okay. So this is the reaction. Now here in the left hand side we have 2 moles of water, right? 2 moles of water to undergo complete oxidation, you require 4 moles of electron. 4 moles of electron means 4 Faraday. So for 2 moles you require 4 Faraday. Therefore for 1 mole of electron you require 2 Faraday. Okay, in Coulomb 2 into 96,500 you will get some answer. Okay, 2 into 96,500, it comes out as 1,93,000. 1,93,000 coulombs. Right? Is this clear, student? Any doubt in this?
So can we leave it in Faraday itself?
But the question is given Coulomb. Just go through the question carefully.
Okay,
How
sir,
much
yes.
electricity is required in Coulomb they are asking.
Yes, sir.
So you have to convert. Right? Here just note down this. This is very important, student. Water molecule can undergo oxidation, can undergo reduction. Okay, in some reaction it will undergo oxidation, in some places it will undergo reduction. Right? To understand the oxidation of water molecule, remember this. For oxidation of water, first we split water into H plus ions and oxide ion, O2 minus ion. Okay, then this oxide ion O2 minus release 2 electron. Each oxide ion release 2 electrons, so I'll take 2 O2 minus. 2 O2 minus ion release 4 electron and gives you oxygen molecule. Okay, now if I add the two reaction, I will get the overall oxidation reaction. Right? But before adding, in the left hand side I have 2 O2 minus, but in the first reaction right hand side we have only 1 O2 minus, so multiply throughout by 2. Now you add them, so you can cancel the left hand sides. Equal quantities you can cancel, so same quantities you can cancel. So we have 2H2O in the left hand side giving 4H plus O2 plus 4 electron. This is the oxidation reaction of water. Water molecule can also undergo reduction, student. So what is the reduction reaction? For reduction, you split water as H plus and OH minus. Then this H plus ion gains electron. Okay, I'll take 2 H plus ion. 2 H plus ion gains 2 electron and become hydrogen gas, H2, and become H2. Okay, now I'm going to add the two reactions, but before adding, see in the left hand side I have 2 H plus here, but in the right hand side in the first reaction I have only 1 H plus, so multiply throughout by 2. Okay, now you just add them, so 2H plus cancel, so you'll get 2H2O plus 2 electron giving 2 OH minus ions and H2 gas. This is the reaction. This reaction is called reduction reaction of water. When water undergo oxidation, students, oxygen gas is evolved. When water undergo reduction, hydrogen gas is evolved. And one more point, when water undergo oxidation, H plus ions are released in the solution. Okay, when H plus ions are released, pH of the solution will go down, correct? As H plus ion concentration increases, pH will go down. Whereas in the second reaction, OH minus ions are produced. Therefore, pH will increase. Okay, remember all this information, very, very important. Right? Is this clear, student? Any doubt here? Question number 14, 2. 1 mole of FeO to Fe2O3. So FeO, question number 2. Ferrous oxide is given. We need to convert ferrous oxide into ferric oxide, Fe2O3. We need to convert like that. Okay. how to do this conversion. So this is actually FeO is ferrous oxide, where the oxidation state of iron is +2. In ferric oxide, oxidation state of iron is +3. Okay, so how to what amount of electricity is required for the oxidation of 1 mole of FeO to Fe2O3. So FeO undergoes oxidation. So ferrous oxide is converted into ferric oxide by this step. Now here, listen. Question number 14.
So can you repeat it?
Hello? Question number 14 too. I'll just do it once again. See, ferrous oxide is converted into ferric oxide, okay, just by oxidation. So FeO plus O2 gives Fe2O3. This is the idea, right? To balance this, what we should do? Okay, I just showed you how to balance just before, so I'll multiply with the necessary coefficients. Okay, so this is the balanced equation. In this balanced equation, see, iron is in +2 state, and here iron is +3. So that means iron atom undergo oxidation from +2 to +3. Ferrous become ferric. So each ferrous ion release 1 electron and become ferric. Here I have 4. Therefore 4 into 1, 4 electrons. So what does this indicate? 4 moles of ferrous oxide requires 4 Faraday of charge. 4 moles of electron means 4 Faraday of charge. Therefore 1 mole of ferrous oxide, this is the question they are asking, right? 1 mole of ferrous oxide require 1 Faraday of charge. 1 Faraday means 96,500 coulombs, right? Students, is this clear? A solution of nickel nitrite, okay, NiNO3 twice, nickel nitrate, let me read out, I'm sorry. A solution of nickel nitrate is electrolyzed between platinum electrodes using a current of 5 amperes for 20 minutes. What mass of nickel is deposited at the cathode? Okay, a solution of nickel nitrate is electrolyzed between platinum electrodes using a current of 5 amperes for 20 minutes. What mass of nickel is deposited at the cathode? Students, observe carefully. Here nickel, in nickel nitrate will produce nickel 2 plus ion and nitrate ion, NO3, I'm sorry, NO3 minus, not 2 minus, it is NO3 minus, nickel nitrate ion, NO3 minus. Okay, now nickel 2 plus ion undergoes reduction at the cathode. By gaining 2 electron, you will get nickel, right? Now here it is given they are passing current of 5 amperes and the time is given 20 minutes, right? You convert minutes into second, so 20 into 60, you will get seconds, right? Now listen, to get 1 mole of nickel, students, observe carefully, to get 1 mole of nickel you require 2 Faraday. Okay, 2 Faraday means 2 into 96,500 coulomb. Okay, so 2 into 96,500 coulomb of charge will give 1 mole of nickel. Okay, 1 mole of nickel. What is the molar mass? Molar mass is not given here. Let me just check it out. 1 mole of nickel means molar mass of nickel, also nothing but atomic mass, which is 58.69. Let me take it as 58.7 grams. 58.7 gram. So if I pass this much coulomb, I will get 58.7 gram. But now we are passing 5 ampere current for this much second. So what is the quantity of electricity? Quantity of electricity equal to 5 amperes into 20 into 60 seconds. So you will get 5 into, so you have to multiply this, you will get 100 6000, right? 6000 coulomb, correct? 5 into 20 is 100. 100 into 60 is 6000 coulombs. So now we are passing 6000 coulomb. If you pass this much coulomb, you will get 58.7 gram of nickel. If I pass just 6000 coulomb, how much will deposit? Right? So I'll write here. So 6002 into 96,500 coulomb will deposit 58.7, right? 58.7 gram of nickel. If I pass 6000 coulomb, how much will deposit? Very simple. 58.7 divided by 2 into 96,500 into 6000. Okay, which will give me, we will get a value 58.7. One second. Yeah, 58.7 into 6000 divided by 2 divided by 96,500 coulombs. I am getting an answer 1.824. 1.824 grams. Take 2. Is this clear? Student, question number 16. 3 electrolytic cells A, B, C containing solutions zinc sulfate, silver nitrate and copper sulfate respectively are connected in series. A steady current of 1.5 amperes was passed through them until 4.5 gram of silver deposited at the cathode of cell B. How long did the current flow? What mass of copper and zinc were deposited? Okay, it's a very simple question actually. It is based on Faraday's second law. Okay, question number 16. Students, observe carefully. So we have 3 containers. The first container contains zinc sulfate. Second cell contains silver nitrate. And the third cell contains copper sulfate. Okay. Now it was given that a steady current of 1.5 amperes was passed through them until 4.5 gram of silver deposited. Okay, so what is the amount of silver deposited? 4.5 grams. Right? And what is the current passed? Current in ampere? 1.5 amperes. Right? Now what we have to do? We need to find out how long did the current flow. Okay, you know very well. Mass of substance from Faraday first law. From Faraday, according to Faraday first law, mass of substance deposited, okay, is equal to Z into I into T. Okay, mass of substance deposited is Z into I into T, where Z is called electrochemical equivalent. M is equal to, what is electrochemical equivalent? Equivalent mass, okay, or 1 gram equivalent. It's nothing but equivalent mass. Equivalent mass divided by 96,500 will give you Z. Z into I into T. Now mass value is given for 1.45 gram. Equivalent mass of silver nitrate. Okay, here what is actually depositing? Silver ion, right? Silver ion gaining electron and becomes silver. So the deposited species is silver. For silver, equivalent mass is 108. Okay, for silver, atomic mass and equivalent mass are same because 1 electron is involving. Okay, so equivalent mass is 108. So I'll substitute the values here. So what we'll get is, so how much mass is deposited, which is 1.45 grams into equivalent mass of silver is 108 divided by 96,500 into current passed through the solution is 1.5 amperes into time we need to calculate, because the question is how long did the current flow. So we need to find out the T. So T is equal to 1.45 into 96,500 over 108 into 1.5. Right? So if I simplify this, I will get some value in seconds. Let me just tell you. 1 second, student. 1.45 into 96,500 divided by 108 divided by 1.5. Yeah, it comes around 863.73 seconds. If you want to convert this into minute, divide the value by 60. So if I divide this value by 60, I'll get roughly 14.39 is coming. Let me take it as 14.4 seconds. 14.4 minutes. Okay, this much time is consumed, must be consumed to deposit 1.45 gram of silver. Okay, students, is this clear? Right, according to Faraday's second law. So what mass of copper is deposited? Mass of copper deposited. How to find that? You know very well, according to Faraday's second law. Okay, mass of silver deposited divided by equivalent mass of silver. Okay, mass of copper deposited divided by equivalent mass of copper. This ratio is same. Irrespective of the species, this ratio is same. Mass by equivalent mass is same. This is what we call as Faraday's second law. Now, what mass of silver deposited? It is given 1.45 gram. Equivalent mass of silver is 108. Okay, we need to find out mass of copper deposited. Okay, equivalent mass of copper. Copper is actually present as copper sulfate in the container C. So copper sulfate contains cupric ion. Cupric ion gains 2 electrons and become copper. Okay, so to get equivalent mass of copper, what you have to do? Take the atomic mass and divide the value by 2. Okay, atomic mass of copper is 63.5. Atomic mass of copper is 63.5. Divide the value by 2, so you will get 31.25. Am I right? 31.7 something. 31.75. Right? Now you can find mass of copper from this. Mass of copper equal to 1.45 into 31.75 over 108. Okay. So what we'll get here is 1.45 into 31.75 divided by 108. It gives me a value 0.426 grams. 0.4262 actually is coming. 0.4262 grams.